Okay, we've done sections 10.1 and 10.2. Now we're going to get to 10.3. Strengths of acids and bases. We've talked about strong electrolytes and weak electrolytes before. They're things that dissociate completely, or in some cases not completely. Well, acids and bases are electrolytes. They, whatever their compositions, well, their compositions are related, of course, but acids and bases, an acid in water is going to increase the hydrogen ion concentration. A base in water is going to increase the hydroxide ion concentration in water. So you might reason that, well, some things are going to be better at it than others. We've already talked about how HCl, hydrogen chloride, dissociates completely in water. Hydrofluoric acid is actually the only halogen acid that's a weak acid. Well, let's look at the chemistry of it here. Go back to a strong acid, and by the way, this is here's a couple of chemical equations, a couple of mistakes that I didn't miss. These have been fixed. Okay, hydrogen chloride, or HCl, in water ionizes completely to H3O plus and chloride. That's it. I mean, it goes completely. You don't really have any. You don't have any HCl molecules in solution. I did mention the last time that you probably have, once in a while, very briefly, for a brief fleeting incident, there's an HCl molecule, but then it encounters a water molecule and it dissociates again. Weak acids, on the other hand, dissociate only slightly in water, and carbonic acid is one of them. It will dissociate in water to give hydrogen ion and bicarbonate ion, or hydrogen carbonate ion. Or you should know that from, and you should know that from talking about the polyatomic ions, hydrogen carbonate versus carbonate, hydrogen phosphate, dihydrogen phosphate, and so forth. And then regular phosphate. So there is a difference. These acids do behave differently, and some, a little bit of, not really trivia, but I did say that acids and there's acids and bases in other solutes or solvents, and in what is a strong acid in water might not be a strong acid in, let's say, sulfuric acid. And even sulfuric acid is not necessarily a strong acid in, there are actually even stronger acids than sulfuric acid, but that's other solvents, that's other media, that's really advanced chemistry, and that's not something. There are practical applications for some of this stuff, like they call them super acids, but we're not worried about that here. We're just worried about aqueous solution. This is biochemistry after all. But anyway, strong acid dissociates completely, weak acid dissociates only slightly. Here's a HI, hydriodic acid, that it dissociates into ions 100%, gives large concentrations of hydrogen ion or hydronium ion, and the anion, well, in this case HA being a generic version of an acid, it's A-. And there's the equation for hydriodic acid. It goes to completion, goes essentially to completion. Okay, if you have hydrogen iodide in water, you have hydrogen ions, and you have iodide ions, pretty much. Now here's a rather comprehensive table of common acids and bases, and you see the strong acids are hydriodic acid, hydrobromic, perchloric, hydrochloric, sulfuric, nitric, and hydronium ion. Hydronium ion is the strongest acid that can exist intact in water. So all these other acids, these stronger acids, they dissociate. They don't exist as that. They're completely dissociated. You don't have nitric acid and sulfuric acid and so forth. You have hydrogen ions, hydronium ions, and nitrate ions. And sulfuric acid, you have hydrogen ions and hydrogen sulfate ions, bisulfate, that HSO4 minus. And the point with the strong acids is that the strong acids, another point that they make here is that strong acids have weak conjugate bases. The conjugate base of sulfuric acid, which is either, well, hydrogen sulfate or bisulfate, which is HSO4 minus, to a less extent, well, the sulfate itself is also going to be around, but that's a bit weaker in acid, as you could probably realize. But HSO4 minus has very little tendency to accept a proton. Iodide ion has very little tendency to accept a proton. So when they get in the water picks up the protons that are available, and they pretty much stay as hydronium ions. And of course, well, weak acids, we're going to talk about that later, some weak bases. So there's the six common strong acids. There's hydriodic, hydrobromic, perchloric, hydrochloric, sulfuric, nitric, and then an additional hydronium ion, which makes a 7. Weak acids, you only get a little bit of dissociation. In fact, very, very little. There's a fraction of a percent of hydrogen fluoride molecules in solution are going to ionize in this reaction. So, and you see there's the double-headed arrow there indicating an equilibrium where it's actually going in both directions, pretty much. So there's only a few molecules dissociate. Most of the weak acid remains as the undissociated form. That's the same thing with acetic acid, which is the acid in vinegar. The concentrations of hydronium ion and the concentration of the corresponding anion are small in this case. So we go back to this same table 10.3, which the relative strengths of acids and bases. And you see you have hydrogen sulfate, phosphoric acid, nitrous acid, and so forth. And a point about hydrogen sulfate, and I'm going to go to the whiteboard here to talk about that. Sulfuric acid, you can see it's 2 hydrogens on it. And in principle, well, it's plus water. This is all aqueous liquid. In principle, it can give you 2 H3O plus, so there's going to be 2 of these, plus back off here, SO4 2 minus, in principle. But if you think about it, when you get to the first one here, H2SO4, I'm going to leave the water out for now, to H plus HSO4 minus. This here, the bisulfate or hydrogen sulfate, is a very weak base. It has almost no tendency to want to go back in this direction and get a proton. It does not have but it can still act as an acid, so it can actually go further to another hydrogen ion plus sulfate. This one, yeah, if you think about it, you're going from hydrogen sulfate to sulfate, you're removing a hydrogen ion, a positively charged hydrogen ion, from something that's already negatively charged. So this sulfate is going to have a little more of a tendency to want to hang on to a proton, or pick one up somewhere. So this is going to be the conjugate base of sulfuric acid. This is going to be the conjugate base of hydrogen sulfate. So these things do work in steps. All right. So in the case of hydrogen sulfate, the sulfate is actually a reasonably strong base. It's not anything like not like ammonia, definitely not like hydroxide, but it's relatively strong. It's definitely stronger than the conjugate bases of the strong acids up above. Phosphoric acid is the same way. Nitrous acid, they're stronger. Their conjugate bases are a little bit stronger. They can hang on to protons a little more tightly than a stronger acid, than the conjugate base of a strong acid. I'm throwing a lot of stuff that's probably confusing. You need to sit down and think about this. Strong acid, weak conjugate base. Weak acid, strong conjugate base. So that's just some things to keep in mind. Those trends occur, and then they said the relative strengths of acids and bases. There's really no those things are mostly acids, but they do have some negative ions in there which can act as, well, bicarbonate can act as an acid or can act as a base, because it has a proton that, or hydrogen that can be lost as an ion, and it also has a negative charge that could actually pick up a hydrogen ion. So bicarbonate is it's a significantly strong base. You have to be careful I have to be careful when I'm talking about strong and weak acids and bases, because in one context a strong base, hydroxide is a strong base. In another context, bicarbonate is a weak base, but in some contexts you would consider it a strong base. But hydroxide is really the strongest base that's going to exist in water solution. But there can be other bases. You see how the Bronsted-Lowry scheme has greatly expanded what we call an acid or a base. So we have another, just repeating what we're already saying. In a hydrogen chloride solution, the strong acid dissociates 100% to form hydrogen ion and chloride ion. Acetic acid, HC2H3O2, is mostly acetic acid molecules and a few ions of hydrogen ions and acetate ion. So we've been talking about acids, now we talk about bases. As I said, they're hydroxides. Strong bases are hydroxides, but then they all lie on a continuum. Okay, the hydroxide's going to be the strongest, but you've got a lot of anything with unshared pairs of electrons, or anything with a negative charge, is going to be capable of accepting a proton, if to some degree. So hydroxides dissociate completely in water. If you have potassium hydroxide, sodium hydroxide, calcium hydroxide, you dissolve it in water, and it's going to be potassium ions and hydroxide ions, sodium ions and hydroxide ions, calcium ions and hydroxide ions, that sort of thing. And you see some representative strong bases there. Weak bases tend to be weak electrolytes, and this is a slide that I didn't really like because of that second entry there, but I left it in, figuring I could explain it. Ammonia is a covalent compound, and it has a very little tendency to form ammonium hydroxide. And ammonium hydroxide is ionic. Of course, that's going to be an electrolyte, so ammonia is going to be a weak electrolyte. With sodium carbonate and sodium phosphate, it's what they say about those are ionic compounds. What they are weak at doing, they're going to be electrolytes. What they're really weak at doing is picking up a proton. The carbonate is going to be very weak at picking up a proton to give you hydrogen carbonate and hydroxide ion. So In sodium carbonate in water is going to be mostly sodium carbonate. Sodium phosphate in water is going to be mostly sodium phosphate. There'll be a little bit of hydrogen phosphate. There'll be a little bit of hydrogen carbonate, bicarbonate in there, but they don't do that reaction. Like if you take in the bottom reaction with ammonia, if you replaced it with carbonate, if you replaced the ammonia molecule with carbonate ion, and you had the reaction giving you bicarbonate, that would really take there wouldn't that reaction would happen a lot. It just because carbonate is a weak base and phosphate is a weak base and so forth. That's be careful with that slide because I say sodium carbonate and sodium phosphate are strong electrolytes, but ammonia, they have a very weak tendency to react with water, to act as bases in water to accept protons or hydrogen ions. So let's identify these as strong or weak bases. These are HBr, HNO2, NaOH, H2SO4, and copper hydroxide. In this one, in identifying strong bases and weak bases, strong acids and weak acids, a lot of it's really going to be memory. I will say that in the acids where there are sulfate, where it's some central atom and a number of oxygens, the more oxygens there are, the stronger the base. But there's not really many other generalizations you can make like that. You simply have to know that this is a strong acid or a weak acid. You need to know that hydrofluoric acid is a weak acid. You need to know that hydrochloric acid is a strong acid or a weak acid, because really in the chemistry of these things, hydrogen fluoride, there's why it's a weak acid is going to be a little more subtle than you might expect. But anyway, so how do these things work? Well, let's take a look at them and think about it. Well, HBr, we know it's a strong acid. Okay, hydrogen bromide. We've seen that. That's on that list. HNO2, that's nitrous acid. That's on the list of weak acids. Sodium hydroxide, it's a metal hydroxide, and it's a strong base. Sulfuric acid, we know that it's a strong acid. A copper hydroxide is another one. I don't know why they actually put that in there, but copper hydroxide is very insoluble in water, and so you're really not going to get a lot of it. It doesn't really have a tendency to dissolve, so it's not going to have a tendency to dissociate, so you're going to call it a weak base. Pretty much something to remember. I said you have to remember some of these things. The alkali metal hydroxides, that's lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide. Have I missed any? Well, francium, but that's very little francium around. They're going to be strong bases, those hydroxides. The alkaline earth metal hydroxides, well, calcium, strontium, barium are going to be strong bases. So those are going to be strong bases. Most of the other hydroxides are the hydroxide ions are going to be held fairly tightly by the central atom, by the metal ion, and they're not going to tend to dissociate a whole lot. So that's something that really kind of surprised me when I saw that slide, but it is a weak base, as you see here. So you only have one weak acid, that's nitrous acid, and the others are strong acids. And then you've got one hydroxide, it's a weak base, is a strong base, and one is a weak base. This one identified a stronger acid in each pair. Well, you have you have the nitrous acid or hydrogen sulfide, you have to pretty much know, you have to know that list. And nitrous acid is going to be the stronger acid. Just look on the list. You look in the table 10.3 and just see where it shows up on the list. So which is the stronger acid in each pair? Well, HBr. I mean, I already talked about how that the second hydrogen coming off of carbonic acid is going to be tougher to get off than the first. And you already know that carbonic acid itself is a weak acid. So if that's a weak acid, then, and you already know it's a weak acid, already know hydrogen bromide's a strong acid, then the bicarbonate has to be the weaker of the two. So HBr is going to be the stronger acid. So we have HNO2 and HBr, and then H3PO4. That's hydrogen. Phosphoric acid is a weak acid, and we remember hydronium ion is actually listed as a strong acid. So hydronium ion is going to be the stronger of the acids in that case. And we get, see, HNO2, HBr, and H3O plus. All right, this is strengths of acids and bases, and we're going to be moving on to acid-base equilibria. I'm going to say one thing, just sort of as an aside, just a footnote or something like that. We have not exhaustively covered all the different the acid-base conventions. We talked about Arrhenius and we talked about Bronsted-Lowry. There are others. And just to mention, you remember that we talked about Bronsted-Lowry acids as hydrogen donors and Bronsted-Lowry bases as hydrogen ion acceptors. So hydrogen ion transfer is the key feature, is the key focus of Bronsted-Lowry. Arrhenius is, well, we mentioned it's produce hydrogen ion, produce hydroxide ion. There's another one. Where we say with Bronsted-Lowry, they're talking about the transfer of protons, proton donor, proton acceptor, hydrogen ion donor, hydrogen ion acceptor. There's something called the Lewis acid base model, where you have bases are electron pair donors and acids are electron pair acceptors. Now you don't see these in water that much. Lewis acids are largely for situations where you don't have water around, because the water really changes, because of the fact that water can act as an acid or a base really changes the whole dynamics of the situation. But there are others where a situation like, well, I won't get into those, but I'll say like boron trichloride, for example. Boron trichloride, you're not going to think of that as an acid or base at all by the conventions you know of. But or boron trifluoride actually is a better one, BF3. That is a very strong Lewis acid. And you have Lewis bases, or like ammonia is a Lewis base, and a lot of other things. But we're really not worried about those, just in case by chance you encounter something where you see something is called an acid or a base, and you look at it and think, well, that doesn't have hydrogen. That doesn't hydrogen, no hydroxide. It can't do that. How can it be an acid or a base? Well, there is another major classification of acids and bases that we're not going to deal with in this course. Again, we don't need Lewis acids because we're in aqueous solution. We're talking biochemistry here. Living things are in water. They're not in whatever. They're not in tetrahydrofuran. They're not in diglyme or whatever. So just know that they exist. Okay, that's it for section 10.3. We're going to get on to section 10.4 and keep going here.